we're rolling. Hello, everybody at home and here. Today, we are going to continue with some of the stuff that we were doing on Thursday, and it's definitely related to these trends. Now, one thing that we already know how to do at this point, is we already know how to list atoms in order of their size. And the very smallest atoms are up here in the upper right-hand corner, and the very largest ones are down here. So that gives us two trends. One, you get smaller as you go to the right, and two, you get larger as you go down and add another energy level. Now, the reason we get smaller as we go to the right is these atoms have more protons, right? So as you're going across a period, you know, lithium is 3, 4, 5, 6, 7, 8, 9, 10. That's how many protons are in the atom. So as you're moving across, you have a stronger and stronger magnet inside of your atom pulling the electrons in. So it seems sort of opposite what you would imagine, but as the atom's getting bigger, it's actually getting smaller. Does that make sense? As far as the field that the electrons take up. So since we have these two trends, smaller and larger, then you end up with a diagonal trend. So like a legitimate question would be like, can you name two atoms that would be almost the exact same size as magnesium? And you'd say, well, scandium and lithium, because they're on the diagonal. Does that make sense, everyone? Okay, and again, this is a chart that's probably made by Linus Pauling, and this is a good way to think about it. It's a nice representation of the atoms. Okay, so what is an ion? An ion is a charged atom, all right? And we have cations and we have anions. And at this point, this is just a little bit of a review. So here is a big old beryllium atom, boom, all right? If it was a Bohr model, it'd be 2 and 2. It's a beryllium atom. Now, beryllium has 4 protons in the nucleus and 4 electrons. So if another atom comes near this, and this other atom is very strong, it could end up taking one of these electrons away, okay? Then you would end up with beryllium plus 1. Why is that? This beryllium atom used to have 4 protons and 4 electrons that all canceled each other out, okay? It used to be neutral. But when that other atom came near and took this electron, now you have 1 extra positive charge, and that's what beryllium plus 1 means. Positive atoms are called like cathode, cations. Batteries have 2 different posts on them. The positive post is the cathode, the negative post is the anode, all right? So when this atom is ionized, what did we just do? This atom was just ionized, okay? And that's the English spelling. American English, you're going to see it written as ionized with a Z, okay? Right? So this atom was just ionized. It had an electron taken, and now it's charged. So what would happen is this bad boy right here would get smaller. The field with which that electron circulated the atom would get smaller because there's still 4 protons here, yet there's only 3 electrons. So there's a lot of pull for only 3 electrons, right? Now what that will be called, and here's our new information, right now it's no longer review, what that will be called is the first ionization. That's the first ionization, when we took the first electron. So the first ionization of beryllium would produce beryllium plus 1, and it would make the atom smaller than the original atom, right? Does that make sense? So this is the first ionization. Now here's, if you're still awake and you're still with me, here's the thing. The second ionization, see there's still a single valence electron here floating around the outside. The second ionization is going to be a bigger deal because now we're going to jump down and the atom's only going to be that big. And now it's going to be beryllium plus what? Plus 2. Does that make sense? So the first ionization creates beryllium plus 1, which looks like a lithium atom. Here's our good old-fashioned beryllium. And then after the second ionization, you have a huge reduction in size because now this whole outer shell of electrons is gone. Beryllium plus 2 looks like helium. And the second ionization has created a very, very large drop in size. Does that make sense to everyone? Okay, now let's look at something else. We talked about this thing being ionized. Okay. There is something called ionization. I'm going to use a Z this time. Ionization energy. You want to write that term down. Ionization energy. People, if you're at home, you better be paying attention because this is important stuff, right? It's important stuff. Ionization energy. All right. Ionization energy is the amount of energy it takes to steal one of these electrons. Okay? The amount of energy it takes to steal an electron. The amount of energy it takes to turn this atom into an ion by forcing it to lose a valence electron. Okay? So if we look at these three atoms we have here, which one of these do you think would be the easiest to ionize? Beryllium, beryllium plus 1, or beryllium plus 2? Which one of these three would have the lowest ionization energy, would be the easiest to steal a valence electron from? And remember, the positive charge is in here. Okay? Positive charge is in the middle. Which one's going to be the easiest to mug? Sir? That's exactly right. Here's beryllium. It's the largest one, and these electrons are way out here. There's 4 protons and 4 electrons, so it's neutral. This would by far be the easiest to steal from. Look at this one right here. It's smaller. These electrons are actually closer to the nucleus. And I know this is not a magnet, but the math is exactly the same. Aren't magnets much, much stronger the closer they are together, right? Magnets that are apart are exerting almost no forces on each other, right? Well, it's the same thing with positive and negative charges. The distance between them is exponentially important, okay? In the math equation, there's a 1 over r squared, radius squared on the bottom. So their distance is hugely important. So this would be the easiest to steal from. Which of these three would be the hardest to take an electron from? What do you think, Sullivan? That's right, beryllium plus 2. You know why? There's 4 protons in here. 1, 2, 3, 4. There's only 2 electrons, and look how close they are. You're not getting those. You're not getting those electrons. Okay? So this is beryllium. This is the first ionization of beryllium. This is the easiest one to do. It's harder to do this one, and you're not going to do it again. You're not going to create a third ionization of beryllium because you're just not getting those. Does that make sense? Okay. Let's talk about atoms that are not ions. Let's take a look at the periodic table. Let me put the blank periodic table up here real quick, and that'll help us out. So if we look at the blank periodic table, I really like this one. If we look at the blank periodic table, there's a trend. Remember, this is the smallest. This is by far the largest, right here, francium. All right. Well, let's also think about the Bohr models. This Bohr model right here, I'm only going to draw the outer shell, okay? This Bohr model right here would have 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. This one right here would have 7, 2, 3, 4, 5, 6, 7. This one right here would have 6, 1, 2, 3, 4, 5, 6. This one would have 5, nitrogen, 1, 2, 3, 4, 5. Carbon would have 4. Beryllium would have only 3. That's boron. Beryllium would have only 2. And lithium would have only 1 valence electron, right? Now, if we're just looking at these guys, and we know that the magic number in the outer shell is 8. What do I mean by that? Does anybody in here know what I mean by the magic number is 8? 8 is the maximum amount of valence electrons you can have. And if you haven't noticed, if you make any Bohr model, you'll never end up with more than 8 in your outer shell. 8 is full, okay? So if you look, we go from a full valence shell all the way down here to having only 1. Which of these on this chart do you think would be the easiest to steal an electron from? This smaller one that has all 8 valence electron, or this larger one with only 1 single valence electron? Who's going to be the easiest to steal from? Is it going to be lithium over here, or is it going to be neon right here? What do you think, Sam? Who's going to be the easiest to take an electron from? Absolutely. Going to be much easier to steal from these guys for 2 reasons. One, they only have a single valence electron. And number 2, they're larger. Isn't lithium larger than fluorine? Okay? And fluorine and neon. And neon has 10 protons. And lithium only has 3. So let me move this and show you like this. Let's take a look straight up at these 2 different atoms. Lithium over here, I'm going to make some approximate size. Here's lithium, and over here is neon. Now you're a magnet, okay? An electromagnet. You have an electromagnetic pull. Let's say this is it. And you put it near this guy, or you put it near this guy. Which one of these electrons, this one, I'm just going to pick one of these, or this one, which one are you more likely to be able to rip away from the atom? Yeah, this guy right here. Does that make sense? So lithium has a lower ionization energy than neon. And now someone in here, neon has a higher IE, higher ionization energy. So someone just said, Mr. Perkins, it's kind of like a pattern. I'm seeing that pattern again. And I would say, yes, you are. You are seeing that pattern again. And here it is. If we go back and look at Linus Pauling's chart of atomic radius, it also works perfectly with ionization energy. Ready? These guys will be the hardest to steal an electron from. They will have the highest ionization energy. Down here, these guys will be the easiest to steal an electron from. Look, francium has 7 shells, and in its outer shell, there's only 1 valence electron. You could easily steal from francium. Does that make sense? So the trend that you're seeing here is also the same for ionization energy. Ionization energy gets higher as you go to the right, and it gets lower as you go down. Okay? Now there's one other point. This video is getting kind of long, but I'm doing the best I can. There's one other reason that these larger atoms are easier to steal from. And it's a very simple concept. Do you remember how the alkali metals can't even get wet? You can't even get them wet. They like burst into flames and cause explosions and go crazy, right? Well, let's take a look at some alkali metals. Here's lithium, right? And then here is sodium. And then here is potassium. Now, which one of these guys do you think is more likely to lose their outer electron? That dash isn't supposed to be there. Which one of these guys do you think will lose their outer electron most easily? Yeah, this guy right here. Potassium gets wet, it's like this, oh, boom, immediately. And the reason it's more reactive than sodium and lithium is this valence electron is way out here. It is very, very far, so the magnetism, electromagnetism, the pull towards the nucleus isn't as strong. Does that make sense? The distance between the magnets is greater, right? And there's another big reason right here, and this is a term you need to write down. Electron shielding. And that sounds like it's complicated, but it's not. You want to write that down? Electron shielding. All right? Electron shielding. And here it is. I normally have funny things to say about this, but I'm not going to say them because I'm trying to keep this video short. Here we go. Bip. Bip, 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 bip. 1, 2, 3, 4, 5, 6, 7, 8. And potassium, right? 2, 8, 8, 1. Potassium, number 19. Everybody like that? Right? Okay. Now this guy right here, this outer electron, is attracted to the nucleus. Right? But if electrons are attracted to protons, right? Because these opposites attract, what would be true of two electrons? Opposites attract, and like charges do what? Repel. I was a kid, I used to play with my little toy trains, kind of like the Thomas trains, right? And sometimes I'd turn one backwards, and I'd push them close to each other, and then they would keep pushing apart, right? And I thought that was really cool. Well, electrons are doing the same thing. These electrons, this electron right here, this valence electron, is trying to be attracted to the nucleus. But look at all these other electrons in the way. They're pushing it away. Does that make sense? The other electrons that are in closer orbits are shielding this guy from the nucleus. So he's attracted to the protons, but also repelled by all those electrons in the way. That's what electron shielding is. And the bigger the atoms get and the further these valence electrons get out, the more electron shielding there is. Does that make sense? Right? And I used to be like this. I used to tell this story. I'm going to tell it. It would be like girls. If all of a sudden there was an announcement on the intercom, and I'm just going to pick somebody, that Zac Efron was in the lobby, okay? And then you were like, what? And then, I'm like, hey, everybody calm down. And then, all the girls just like barrel over me and knock me down and go running out the door, okay? And they run downstairs to see Zac Efron. What would the one problem be when you got downstairs, girls? Besides the fact that he's way too old for you. What would the other problem be? You literally can't imagine this scenario. The other problem would be that all the other girls ran down there too. So when you're trying to get to him, all the other girls are in your way. That's electron shielding. Does that make sense? I'm going to pretend that you all think that's funny and that you're smiling under your mask instead of just giving me the dead eyes, okay? All right, so I'm going to keep moving, all right? Going to keep moving. Electron shielding, I think, is simple enough. I don't need to talk about it anymore. If you're at home and you don't understand electron shielding, play the video over again, right? Other electrons are getting in the way of the outer electrons. That's electron shielding, okay? So we've talked about ionization energy, and here's the exact opposite thing, right? The opposite of ionization energy, and I know this is getting long, we're about to do a worksheet, is called this. Ready? Electronegativity. You want to write this word down. Whew, I'm on 20 minutes. This is getting long. Electronegativity. People at home, you can play this at 1.25 speed, okay? Electronegativity. Ready? Electronegativity is the opposite of ionization energy. Ionization energy is how much energy it takes to steal an electron from you, okay? Electronegativity is how strong are you at stealing other atoms' electrons. Does that make sense? Electronegativity, ability to attract electrons from other atoms. I like to say this as electronegativity is how strong a magnet you are, how powerful an electromagnet you are as an atom. Okay? I'm going to make it quick. I'm going to post a short set of PowerPoint notes that you can look at again, or people at home can look at, about what I've been talking about for the last 20 minutes. But in short, I'm going to show you the most electronegative atom on the periodic table, and then I want you to think about why, okay? The strongest magnet on the periodic table, the biggest bully of all the neutral atoms, is fluorine, okay? Fluorine is the bee's knees for electronegativity. And I'm going to show you a picture of it, and you see if you can tell me why. Here's fluorine. Bip. 2, 3, 4, 5, 6, 7. There's fluorine, and here's lithium. 1. Here's lithium, and here's fluorine. You know why it's easy to steal this electron. There's a single electron, and it's far from the nucleus. Why is this atom very good at stealing electrons? Take a look at it and tell me. Give me one reason, someone. It only needs one more electron. That's an excellent observation. It only needs one more. If it just had one more electron, then it would feel like neon and it would be perfectly happy, right? There are also 9 protons in the nucleus. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And tell me another obvious difference between these two guys. It's obvious. Their size. Look how small this is. So all of these electrons, all of fluorine's electrons, are very close to the nucleus, very close to the protons. Does that make sense? So check this out. If I took this fluorine atom and I drew it right here, there's only 3 protons here, and there's 9 protons here. Where's this electron from lithium going to go? It's going to get stolen, and now it's going to become the last electron for fluorine. Boop. Now you have fluorine -1 and lithium +1, and this whole shell is gone. And that right there is ionization. This one is very electronegative. It stole the valence electron. It only needed one more. Does that make sense? So the most electronegative atoms are the smallest ones. So if we're looking here, fluorine is the most electronegative atom. And you're like, Mr. Perkins, helium is smaller. Helium's not going to steal electrons from anyone because it already has a full valence shell, right? Helium has one shell with 2 electrons, and you can't put any more electrons there. So just like with ionization energy, fluorine has the highest ionization energy, and cesium has the lowest ionization energy. Fluorine is the most electronegative. It's the strongest magnet. And cesium would be the weakest magnet. That's it. Does that make sense? Now I can end this very long video. People at home, good luck.